Hello, it's Duncan. As a TDD zealot, today's episode was quite difficult to edit. I've already failed in one attempt to write a JSON parser using TDD when the simple approach I was taking ran into the complexity of parsing arrays. Starting again with a state machine made significantly more progress, but I do seem to be fighting to stay on top of new requirements as I introduce them. I should say that I'm not a computer scientist and have no previous experience writing parsers, so this is a genuine experiment, not a rigged demo. Compared to learning about proper parsers, probably starting with a tokeniser, my gut feel is that this approach may well yield a very efficient parser that is tailored to the specifics of JSON. But as this episode shows, the complexity of the code tends to get out of control pretty quickly while I get test passing, and I don't always manage to refactor enough to feel confident that things are going to turn out all right in the end. Well, let's address the elephant in the room. Duncan, who's an old man, forgot what the separator was in JSON. So I merrily wrote a whole bunch of equal signs here rather than colons. Luckily, we have an abstraction for the separator and it's not used very much in our code. So I think we should just be able to start here and select all of our equal signs in the tests, but not that one which is in code. Replace them with colon. Run all of our tests. That fails. I'm not sure in the way that I'd expect, but it does fail. So let's go back to our implementation. This is where we have a literal equals. Let's see if there are any others. No, that was the only one. So we should be able to change that for colon. Run the tests. Oh, that's an interesting failure. I wonder whether we missed one in our arrays tests. Let's have a look. Arrays tests. Ah, there we are, yes. So if that was a colon, run, we'd be good. And then we can go back. And obviously this is now not equals, this is colon. Splendid. And now we can commit that. Don't know what has changed in Gradle, but this is fix wrong property operator, and we can pretend it never happened. Some issue here, what's that? Oh, who knows? Let's just commit it as Gradle stuff. Right. Now, I like to start each session with a tidy. So let's review what we've got and see what we could tidy up. So our top level here is this parse function. And that sets us up with a parse state, which is ground, which is white space and space between characters at the moment. I'm not really sure what it means. It was just expedient. And then we go through every character in our string and we change the state to whatever our current state says it should be given this character. And then at the very end, we ask whatever state we ended up with for its value and we return that. Now, first thing is, I think I can make this work on char sequence. So a string is a char sequence. And this for each is on char sequence. So we could in fact work on things that were JSON that weren't just strings. So for example, we could express a file as a char sequence. So that might save us reading everything into memory. If it compiles, I'm pretty sure it will run, but we'll just check. And that's all good. Okay, here's our parse state. It's an abstract class, and every parse state remembers its previous state, which may, in the case of the very first one, be null. And I think we can make this private, because we don't expose it in our API, and that means also all of our little classes will need to be private, but I think that's worth doing. There were quite a few of them. Is that it? Yes, it is. Run the tests. Good. Back up to the top. Our ground state is accepting characters and trying to move out of itself, really. If it sees a quote, it moves to string state. Brackets and squiggly brackets give us array state and object state, respectively. And if it's white space, though, we stay in ground, because ground is collecting white space. Comma moves to comma, colon moves to colon, and everything else is treated as a literal. It's a very small thing, but this character as white space is potentially an expensive test compared to these other ones, which are just checking for equality. So I think I'm just going to move that down there. so that we might find a comma and a colon quicker. That shouldn't change anything, and doesn't. Good. And now the value of ground is the value of its previous state if it has one, and if it doesn't, then it's a legal argument exception because it means we've had no significant content at all. We're going to look at what we can say in these exceptions a little bit later. Okay, moving on, literals. Literals just remember all the characters in a string builder. Again, I think we could change the order of these two tests in the when, and we could make that into an expression body. So for a literal, commas move us to ground. Oh, well, we have a comma, so maybe we should put that in there. Does that make everything carry on working? It does. Feels like that's a bit better. White space moves us to ground, otherwise we keep on remembering the characters. And value checks to see whether we're null, true or false, or a big decimal. If we are, it returns the appropriate Kotlin primitive, or a big decimal. And otherwise it throws an exception to say, you thought you were parsing literal, but you weren't really. String state, well, that also remembers all of its characters in a string buffer. And apart from a little bit of jiggery-pokery here around escaping a quote, it generally just appends the characters into its buffer unless it has found a quote, in which case it remembers the quote and returns to ground. And its value is, if it's not terminated with a quote, we throw a legal argument exception. Otherwise, we pull the bits between the quotes out. We know it must have started with a quote and we know it must have ended with a quote, and return that as a string. Array state sets up its own parse state inside it. And it manages a state machine so that it takes characters that it's accepting and passes them to its own little state machine with this parse state as a state. And it's looking to see when it ends, and otherwise it's moving on through the parse states. And when it has ended and we ask for the value, well, it checks to see whether it's complete, that's whether it got a closing brace, and otherwise it takes the sequence of states inside it and derives a list from them. It's all a little bit tacky at the moment, but not as tacky as object state, which does the same sort of thing, but has to deal with comma-separated pairs, themselves separated by a colon. And I think it's true to say we have quite a bit of sort of technical debt in here. And then finally, colon and comma are states that we can't really ask their value, and we're left with this to-do, which is a bit unsatisfactory, but works because we are always filtering them out. So we've got it is ground or it is comma before we end up asking for the value. So there's something missing in our type system for that to-do to still be there, I think. But we still pass the test, so let's check that in as just a tidy. Okay. There was one suspicious thing in our review that's sort of sitting in the back of my mind, and that's a literal accepts comma and white space. But we now know that colons are a separator as well that should take us out of literal. Now, colons are a separator in objects, so we'd expect that to happen in an object if it's going to. But looking at our examples, I suppose that we only have strings before a colon, at least in well-formed JSON. So in well-formed JSON, we can't have a literal and then a colon. I think that it would be good to add a test in here of something like a string to null, butted up against the comma, because I don't think we're checking null in here. So I would expect that still to pass. Let's have a look. And it does. But I think probably we should go in here and say it would do us no harm to interpret a colon as a colon. That's fine. I feel a bit icky about that as a test-driven developer, in that I've made a change and I don't have a broken test to support it. Now we could write a unit test of literal on its own, or we could set up something that's invalid JSON that shows that we need that. But I think that maybe life is too short. I'm going to say that that's the right thing and hope that it doesn't come back to bite me. These sort of unsupported changes are a good place to have their own commit though. So I think this is going to be send literal to colon, even though we don't actually need to. Okay, I think we now parse valid JSON and output Kotlin primitives, lists and maps. So we could potentially use this parser in production. The problem is that we know that it also parses things that aren't valid JSON. Now I'm a bit conflicted about this because when the JSON is invalid at the moment, it makes quite a good attempt at it. So for example, we had this to do in arrays that says show lists need comma separators. What's that about? Well, it's about the fact that expect that parse, if we put in an array with, for example, true, false, banana, I have to escape the quote for that, that at the moment is equal to a list of true, false, and banana. Is that true? Yes, it is, but this isn't valid JSON. We can interpret it. In fact, I think it's unambiguous. Spaces are a fine separator there, but this should fail as a JSON parser. So if we want it to be a proper JSON parser, we're going to have to make it more complicated and in some ways less functional than it is at the moment. I'm going to come back to that one because I think there's a bigger problem right at the top. And that is what happens at the top level if we have several things that are valid JSON just following each other. So that, expect that parse, let's do it with strings, so I'm going to put in triple quotes. So if I put in A, B, C, complete that. So we now have three things. I could put in some white space to make it more obvious. So we now have three top level things. Now that's not valid JSON, but at the moment I think it parses. What does it parse to? Well, I think the answer is the last of the things we find. So that would be a string of C. See whether that's true. No pun intended. And it is. So this should not parse. Now why is that particularly a problem? Well, it also, I'll put it in here, applies to things that are not strings. So we could say A, B, C. Now that will fail to parse. There's the exception. But we only find out at the end of this string. So we could be 100,000 characters into, for example, a CSV file, something like A, comma, B, C. And it's only after 100,000 characters that we discover that we had a problem. I think that is the comma. I've got the problem there. Let's just do that. Yes, there we go. So we've got our not a literal C, but we'll have merrily parsed all of the characters in here, which as it's now a char sequence, could effectively be infinite. That doesn't seem like a good behavior for a parser whose job will probably be to sit looking at input from the internet. So that's the thing I think I'd like to fix first. Okay, I'm going to delete that line for now so that we have some parsing tests, but a couple of to-dos. Oh, but just before I do, I see here, look, there's a to-do that says expect throws legal argument section null colon. I think we've probably got that working a little while ago. So let's uncomment that out and check that it's good. Oh no. And this being a to-do and not implemented, that shows that what's happening is that we're asking for the value of a comma, and that was a point where we said that comma and colon had this issue that we can't ask for their value. So we're failing to parse, but maybe for the wrong reason. But actually, thinking it through, I suspect that this is a case we're about to pick up with what do we do with multiple things at the top level. So in fact, let's take this out of here, and I think after we've done numbers and so on, I'm going to say, let's have a test in here that doesn't allow multiple top level things. I don't know what things are yet, but this is an example of the sort of thing that we want to fix. As is, say, true and false. See how that is. And that's now our only failing test, and it's in the right place. Okay then, here's our parse at the top level. And the issue here is that we can start with ground here, parse out a literal, go back to ground for the white space, parse out another literal, and then we will be the value of the last literal we found. In fact, if we put space in there, we'd go to ground and then that would ask the previous state. And that's kind of because we don't know we're at the top level here and we only ever want one actual state. Now, suppose we could do the same sort of thing as we did with the arrays and the objects, which is to wait until we finished and then check the structure of the linked list of states that we've got. But that's the thing that exposes us to a potentially unlimited input. If we parse an infinite char sequence here, we'll just eventually run out of memory. So instead, I think we can say, let's remember our new state, which is new state. Then we want to throw an illegal argument exception with a message something like cannot have more than one top level result. Let's try that. Oh, that breaks everything except the one thing probably we were trying to fix. Why is that? Oh, well, when we move off of ground in the very first place, we don't want to throw. So we can add in a test there, which is and our state's previous state is not equal to null. And that's this state here, the very, very first one. So is that true? Okay, strings has failed. Why is that? Ah, well, look there. That was one we said shouldn't parse and now doesn't. I think we're taking care of that in our current test, so let's get rid of that. And run. Good. And now, can we give a better error message? Well, I suppose at the very least we could say at what character. So let's write the test for that. So this thing should say, I throw in legal argument exception and the message equals, and we're going to start with that thing. Let's move that over. And we might say failed at, and we're using square brackets to say what the problem was. And in this case, we expect to be failing at the F, I think. So the character in here would be failed at $char. Is that right? No. Why is that? Incomplete assertion. Well, that's a strict problem. So expect throws a thing. Oh, rookie mistake. That should be is equal to. Every assertion library author has that problem. Rerun, and we're good there. And we can say the same thing here. So this should fail at the comma. Nice. I think to be truly helpful, the library should probably know which line and which column the issue is at, but that will need us to keep track as we parse, and doesn't seem like our biggest problem at the moment. Okay then, now we know that we are failing as soon as we diagnose the problem. I guess we can say that if we were to have a space in here, then we don't know we've got a problem until we reach the comma. So is that right? Yes, it is. So I think that's worth a check-in with disallow multiple top level. I'm going to call them entities for want of a better phrase. One to do, and it's this one here, which I think we may just be about to address. Okay, I've actually been sitting and thinking a bit about what to do next. We've got this to do for show lists need comma separators, and I think we're just going to create a test for that. So this is test arrays need comma separators. And the behavior at the moment is that we don't need them. So this space separated list here is parsed correctly. So let's take that out of there and put it in here. And when we try and parse true, false, banana, what we'd like is that it doesn't work. So not expect that, but expect throws. We want our legal argument exception, and we're going to give it the block that is trying to parse. And then as before, we can say something about the message is equal to, and well, that's going to be a string, and I don't know, but it should say something about, I'm just going to say comma for now. And as with our top level state, we'd like this to fail fast. We don't want to go into an array with 100,000 elements separated by spaces and only tell you that there was something wrong at the end of the 100,000 elements. Okay, so we just check that it does actually fail. And it does. So let's wander over into our array start state. Here it is. And the moment we are collecting all the states, that's a linked list attached to ground. And then when we finish the array here, we are taking the sequence of states from the end parse state, and we're using that to derive the contents. Now, when ArraySet accepts a character, we could intercept it and ask whether it's the right sort of thing. So as with the top level, we could sort of look at the transition and see whether it's acceptable to us. But I wonder whether we can actually run our own little state machine in here with different states. We've already seen the state machine model working quite well, but I wonder whether our current ground and comma and so on are just too general. In cases like this, it's often worth a little experimentation just to see how far we can get. So let's go and see ground. And I think I'm going to copy this and put it into array state. So array state will have its own ground state. And that will allow array state to do different things with characters. Okay then. Now the consequence of that is that this parse state is ground and so on is all the one that's private in here. It's going to get a bit confusing, so I think I'm going to rename this to be array ground, just so we can see what is what. Let's see what that does to us. Okay, so things have started going wrong. Arrays may be the simplest of those. Cannot have more than one top level result failed at right bracket. That's a bit strange. Looking here though, at the top level here, when we're done, I don't want to be passing out array ground, I want to be passing out the ground from above us, as it were. So let's try that. Okay, and now we've got different thing, and we're getting illegal argument in array state exception. Let's see which test actually failed. We do seem to be in a bit of pain, don't we? Let's go back. And I think I'm going to undo that array state change. So we can go to a commit and just roll back JSON. Check that we can still run everything that we're not expecting to fail. But I think I'm going to go and disable this test while we refactor, so we know for certain that everything is running when we do. Okay. It looks like we're going to have problems with our two types of ground idea. I haven't given up on it, but one of the problems I foresee is that ground carries the previous state with it. That's this previous parse state that's inside ground here. I quite like the linked list nature of that, but I suspect that it's making things a little bit the wrong shape. One of the reasons for that is this value, which some of our states accept and some don't. And another one is that I think when we get into array state, for example, here, and the same with object state, we've got this sequence of states that we wrote last time, but we're having to get the entire sequence before we can map the values. Once again, we want our array state to fail quickly. So in fact, I think we want to be collecting the values, not the states. We don't want to wait until the end here to go through our states to work out what the values were. It would be better to collect the values up here so that we parse them one at a time. Now, I'm aware this kind of sounds a bit weasel wordy, and to be honest with you, my designs often wander around while I'm trying to find the right expression. My gut though says that it would be interesting to try and get rid of all of these previous parse states. And as we're looking at array state, let's try and do it here. Where are we using them? Well, ultimately in this sequence of states, which is using it.previousState. Okay then, so what if in here we have the private val of our values? That could be an mutable list, and we know that our values can be basically anything, including null. Actually, you know, my brain's gone ahead a bit, and I realize we're going to have some troubles with literals in here if we do that. So at the moment, I think I'm just going to remember the parse states. So we'll call these states. Right. We want to remember them every time we get them. Our first one is ground, though, and we can ignore it. Our last one, well, the last thing that happens here is we return a ground, but this is the end of the array, so we don't need to do anything about states in there. So the only place we need to remember our states is in here. Now we could do the new state, is it the same as the old state, etc. Or in fact we could just say that if states.last, or null in case we don't have one, is not equal to parse state, the new one, then states.add parse state. That shouldn't have broken anything yet, and hasn't. But now when we come to get the value, we should have our list of parse states. So I think maybe we could say not parse state is a sequence of states, but parse states. But in fact we call that just states. Now we still want to get rid of the grounds and the commas, we still want to map it to value, but they will be in the right order, so we don't need to reverse them, and so we don't need to list them. Might that work? Well, it does, and that really shows the value of a good test suite, that we're able to make really quite a fundamental change there and have a good deal of confidence that we haven't broken anything. I think we should be able to do the same thing in object state, so let's copy that. Object state is going to have a list of states. It's going to say add to it if something has changed. And then when we look at the value, we can once again not do parse state to sequence of states, but we can say states filter not, don't need to reverse. Does that work? And it does. So I think that the sequence of states is dead, and it is. And let's go back up to parse state and find who references previous state now. In fact, we can see two of them. We can see we've got one here and one here. So let's try and get rid of those first of all. This one here is in our top level parse. Now this is already a bit of a mess. I think probably deserves a little state machine all of its own. But here we're saying, and state previous state is not equal to null. And what we're really saying there is that the state is not our initial state, this ground of null. So I think what we could do is we could just remember this as initial state, and we could say that and state is not equal to initial state. Is that true? Yes, good. And now where else are we using previous state? Let's just have a look. And I think the answer is probably only here. We are reading it in when previous state, and we are sending out previous state values. It's in fact just these two lines that reference previous state. And they are both in our ground state. Now I'm winging it a bit here, but I think the only place we probably use that is in fact at this top level here, where we may get a ground state at the end. So I think I'm going to try and do the same thing here as we did in our arrays and objects, not because it's the simplest thing, but because if I make the shapes look the same, then there's going to be an opportunity to refactor later. So we're going to do the same sort of thing. We're going to say val states is a mutable list of parse state. We're going to say if states last or null is not equal to our state, states add state. And then down here, instead of asking the state for its value, and if it's a ground state having it chase back its list of pointers, we've got our states here. So we can do the same sort of thing as we did up above, which is something like val filtered is my states dot filter, it is not ground. And now because of all this messing about up here, there should only be one of those, I think, so we should be able to say filtered dot single value. Let's try that. Oh, that fails. Why is that? Well, we may have no elements at all, as in the case of an empty string. What do we want to do with that? Well, we said we were just going to throw in a legal argument exception, and we haven't sorted out the message yet, so that makes our life a bit easier. Go back, so we can say return when filtered is empty, throw illegal argument exception, else a single item's value. Is that true? Yes, it is. Again, this isn't very nice, but our test will allow us to make it simpler later. Okay, here's the question. Is previous state now actually used? Let's just try deleting it and see what happens. Just fix up those compile issues. So that's that one. Now this was ground value, which is going to previous state. And I think I'm just going to say you can't ask ground for its value in the same way as you can't ask a comma or a colon. No previous state for you, no previous state for you, no previous state for you, or you, or you, or you. Does that work? Good. And now we also don't need to take a parameter. And run. Now, what has that gained us? Well, one of the things at least is that things like comma and colon have no state at all. So in fact, they can just be an object. Oh, but they need to be private. And so can colon. So those things that aren't actually collecting anything for us don't need any state at all. Let's just make that expression body to make everything a little bit tighter, and the same thing here. And I think we might even do that. So those are now super simple. Does that break anything? Well, yes, we can't construct them. We just have to pass the object back. Splendid. And the same here. Any more? No. Let's run. Wonderful. And now let's go back to ground. And ground now has no state at all either, so we can make that an object. Fix up the issues, so that is just, we'll go back to our non-stateful ground. Ditto here, and here, and here, and here, here. And bear in mind that each of these object allocations will be being made on our heap. They will take time and memory. So being able to use stateless objects is a good thing for a parser. Let's run that. Oh, I missed one. Did I miss any more? No. Oh! That's the sound of genuine surprise. I didn't expect that to break, but it has. Let's have a look. Doesn't allow multiple top level things. And it looks like we had more than one element when we parsed true and false. Let's see if we can work out why. And I think the answer is in this horrible logic here. Now ground has no identity. There's only the one ground object. We don't know whether a second ground state is going to be the same as the initial state. I think I may regret this later, but I think in here we can just use the size of states. So we can say, and states dot size is greater than 1. That is to say we captured a ground and another. Just see whether that's right. Oh, maybe 2. Still not. Well, I've had to think about this for a bit, and I think the least worst at the moment is to say here that we're not going to accept another result if my states filter it not is ground, like down below, dot size, I suspect probably greater than 0 will do us. What's IntelliJ warning? Oh, well, it says is not empty. I suppose that's okay. Let's see whether that's true. It is. That's good. Once again, this is all getting into a bit of a mess, or I should say even more of a mess. So let's see what we can do logically. Well, we wanted to capture not really the states, but the values of those states. So I think maybe if we were to change this to mutable list of any question mark. Now I think it's on a state change, when new state is not equal to state, that we have a value that we could put into this thing of states, but actually would be values. In fact, let's do this in 2 stages. Let's undo that one, and let's give ourselves a values is mutable list of our any question mark. Now you might reasonably say that, hey, Duncan, the top level can only have one value. Why are you creating values? And the answer is, I suppose that I want to see how well this works here in order to do the same thing inside array and object. Okay, so can we go forward with this? Can we say if the new state is not equal to the state, so say we have a change, the duplication will just deal with it, then we're going to take the old state's value and add it to values. Values.add state.value. Now, does that pass still? Oh no. Why not? Well, I'm betting that it's this, we're getting some grounds. So we're going to do that for now. Is that okay? Still not. What's our issue? Oh, don't understand that. Let's see who's complaining, and the answer is it's ground value. So that's weird. I thought we'd just done that. Back again. Oh, I'm an idiot. In this case, I want it to be that my state is not ground. Getting there, maybe. Now that begs the question of commas and those other things which won't tell us the value, but I'm going to leave that alone for now and say, maybe just here I can say that when my states is empty, that's a legal argument exception, otherwise it's my states single. True? No. What sort of thing that failing with? Parsing an empty string. And here we're saying it's a literal is equal to 42. I think I may be putting the wrong things into that list. Oh, I'm an idiot. That's not states, that's values. You probably saw that. Now we're good, apart from some odd ones. Let's have a look. Parse 42. is a legal argument exception at parse 22. So apparently we had no values at all. And finally, I think the issue is that we're not putting our end value in. Our states are being put in as soon as we change to them, but we only know the values at the end. So it's really quite horrible, but at the end, I'm going to say, if my end state is not ground, add in the value of the state. Does that at least pass? Phew. Now I'm not going to try and defend this code, but I am going to clean it up, so we'll remove that. And not just the assignment, I actually want to remove the states filter. And I think this means that I can do without my states altogether. So I'm going to get rid of that. We don't need to add them in here. And in here, the question we're going to ask is, do we have a value? So at this point, we're going to say values, and values is not empty. Is that true? No. So we'll back out until something does pass. So we would still need the states there. Is that true? Okay, let's go forward in smaller steps. The bit we need to get rid of here is this bit. And we still think that this should be values is not empty. So let's run and see what's actually failed. So we've got a not implemented in multiple top level things. Not quite sure where, because for some reason not really telling us. So let's differentiate between the things that could be throwing that not implemented error. One of them I think is our ground. So that's here. We could say to do ground. Literals we can get a value from. String states we can get a value from. Arrays we can. Objects we can. But colons we can't. As I keep on saying, this is a problem with our types. We obviously need to be able to differentiate between ground, colon and comma, those things that don't have a state, and other things. But for now, it's that phrase again. This is comma. And run and see what we get. And this says an operation is not implemented, comma. So let's have a look. So we're passing true and false, null comma, or null space comma. Well, I'm pretty sure it's going to be one of these two then. Let's go back to JSON, back up to the top. And here I can see we're doing state value when the state is not ground, but we should probably check the state is not comma. And in the fullness of time, colon and other things as well. Does that fix us? No, it doesn't, but we are now getting null. So we expected a failure, but we returned null. And begin to feel like you do when things are going very badly in an interview. Do you just bail, back everything out, start again, or try and go forwards? I'm going to try and go forwards, and I suspect our problem here is that we've parsed this comma, not added it to our states, but not failed either. So if we go back, I think we probably have to say, if the new state is not the state, and the new state is not ground, and the value is empty, then we'll do that. Or the new state is comma. And again, as I say, probably colon as well. But phew, we have something working. So now the question is, can we do without our states? What are we doing? We are adding to them there, and we're not querying anything. So it should be surely safe to remove that. And is, and hence to remove this. And is. I'm getting tired, but I don't want to finish on a rising tide of entropy. So I think what I'm going to do is I'm going to extract an interface out of parse state. So if we say extract interface in here, and we're going to call it not I parse state, but valued. Let's say something that has a value. I'm going to extract value. See what happens. Okay, well, strange formatting, but there you go. So now parse state is valued, but I don't think it should be, because not all of our parse states can yield a value. So now we can take that out of there. Is ground state valued? No. Is literal valued? Yes. Is string state valued? Yes. Is array state valued? Yes. Is object state valued? Yes. And is colon valued? No. So we can get rid of that. And comma is not valued either. And now you can see that it's not compiling, but you can also see that here we could say filter is instance valued. And that would stand in for our not is ground or not is comma. The only problem is that in object state, we're splitting things into 3 with the colon as one of those things. So I think we would need to window this with 2 every 2, and our value is going to be the second one of those. It's a bit of a punt. Let's go and see what else we can fix. So up here, the issue here is not the state isn't ground, the issue here is the state is valued. But now because state is mutable, we can't rely on flow typing here. More horribleness, but I think we're going to say that old state is state as valued, and we can say old state in here. I'm trusting that that will go away at some point, and the same thing is true here, so we will remember this sort of thing. This is value state, state as valued, values add value state. Value. Get rid of that, and this again is if state is valued. Now there's half a chance that that will work. If one more compilation error, and again we have here this is filter is instance valued map it value. And I fervently hope that just means I haven't done a dot value on something at the top, which is just there. This is a problem with having a mutable list of any question mark. Wow. I'm going to lock in this horribleness with a commit that is remove previous state from parse state, making everything worse before it gets better. Does it pass? It does. Now looking at this code, this sort of mess is just the sort of arbitrary nonsense that state machines are supposed to save us from. Will something better fall out of this? At the moment I really don't know. My gut feel is that we're going in the right direction, although maybe I'm not doing it very well. Often I find I need to take a code base, shake it up a bit, change the design, accepting more complication like we have here, and I'm trusting that I'll be able to refactor that complication away when I can see a better model. In terms of goal seeking, I suppose we are coming down from our local maximum into a sort of pit of worseness before we can go up to a higher hill that might express our problem better. As you can see though, at times this is a bit of a random walk, just exploring the area and seeing whether we can find another positive gradient. Of course, the nice thing about software is it's soft, so if this experiment proves fruitless, if I only go downhill from here or I go up, but not as far up as I was previously, I can always just revert in Git. I hope not to have to do that because I've already ignominiously failed in this mini-series, but only time will tell. If you'd like to see the resolution of this not so much cliffhanger as swamp paddler, then please subscribe to the channel to see the next episode. Press the like button on this one, and maybe buy the book that I wrote with Nat Price called Java to Kotlin, a Refactoring Guidebook. Thanks for watching.